Welcome back everyone. So we have been looking at a possible model for generating binary features for a binary classification problem, and we have put down a model where which involves a certain bunch of parameters. Just to recollect what our model was, so we have a box with a coin P which decides what is the label of the data point that is being provided to the user in the training set, and the label can be y equals 1 or y equals 0. And then in the case of y equals 1, we have a bunch of d different coins which with probabilities p11 to p1d. Similarly, on the other side, when y equals 0, we said that we have a bunch of coins with probabilities p01 to p0d. Now, the way the data is generated is first you toss the coin with probability p to decide whether y is 0 or 1, and then you generate the feature conditioned on what y you have seen. If y equals 1, then you toss the left set of coins, d coins, and each coin determines whether a particular feature, binary feature, is 0 or 1. In the example that we looked at, where we were looking at a spam classifier problem, the y equals 1 or 0 corresponds to spam or not spam, and the features corresponds to whether a word is present in your email or not present in your email. So we said that this has the class conditional independence assumption, which is the key assumption, which helped reduce our parameter space from 2 power d plus 1 to 2d plus 1. Right now there are d parameters here, and 1 parameter here. So we have 2d plus 1 parameters. Good. So we have put down this model for our data. For the data, we just observe the data. Now we are assuming that this is the model that generates the data. So now the question is, how do you estimate the parameters of this model? And that's where we ended last time. And what we are going to do today is to see how parameters can be estimated under this model. So, so the parameter estimation is what we will start today. Well, because we need to estimate the parameters, we can use the standard technique of maximum likelihood to estimate these parameters. And what we want to then understand is what kind of estimates do these maximum likelihood estimation procedure give us. So, just to be sure, the parameters to estimate are p1 p1d and p01 p0d. The superscript corresponds to the label, the subscript corresponds to the feature. That's for the set of features, feature based probabilities. Okay, so it's not too hard to do the maximum likelihood estimates, and I'm going to give you what these maximum likelihood estimates are, and it should be fairly straightforward to derive the maximum likelihood estimates by yourself, because we have seen estimation techniques already in detail in this course, and all of these are Bernoulli random variables which takes value 0 or 1, and we already have seen how to estimate Bernoulli parameters. Here we will see what these estimates are, and you will see that these are the most intuitive estimates that you would have expected anyway, right? So here are the maximum likelihood estimates. Let's first start with p hat, right? So p hat is, what is p hat? P hat is trying to estimate the probability that an email is spam or not spam. Now remember, in our discussion, in our way the model is set up, the decision of whether an email is spam or not spam is made first, and then the features are generated. So the features are not going to give us any information about the decision whether spam or not spam, because that coin was tossed completely, that coin's decision or outcome is independent of the others. So what we can say is that, if intuitively also, and you can also work this out formally, that the maximum likelihood estimate for p, which is p hat, should just look at the labels, right? So because the labels are the only things that are decided by this coin with bias p. So, which means that the label should give us the information. So, now what would be the maximum likelihood estimate? Well, you have a data set of 1000 points, which means that you toss the coin with probability p 1000 times to generate these labels, and you saw a bunch of heads, bunch of tails, which means you have seen a bunch of spam emails and a bunch of non-spam emails. So, what would be the maximum likelihood estimate? You should already know this because we have done this before. Pause and think about this, and I will tell you what the answer is, which is fairly straightforward, which is just 1 by n sum over I equals 1 to n yi. It is the sample mean of the labels, which can also be, of course, interpreted as, fraction of spam emails in the data set, because yi is either 1 or 0, and if yi is 1, then it just means our data has spam email, otherwise it has non-spam emails, and then we are just counting the number of spam emails and dividing by the total number of emails. So, it is just a fraction of spam emails. That is fairly straightforward. Now, what would be the maximum likelihood estimate for p hat for let us say y and j? So, what does this mean? This means that so in general, if I say y in the superscript and j in the subscript, it means that I am saying my label takes the value y, which could be either 0 or 1, and my feature takes the value j, which could be any number between 1 to d, right. So, in general, what is going to be the maximum likelihood estimate for when the label is, let us say, 1 and we are looking at the fifth word, right. So, let us say we want to understand what is the bias, best estimate for the bias of the coin, which decides whether the fifth word is going to be present in my data or not, given that the label is spam. Now, what would be the intuitive way to think about that? Well, this probability is going to be decided only by looking at data where the label is equal to y, that is label, let us say, is spam, because the non-spam data has nothing to do with this feature, right. So, because you are trying to estimate the bias of a particular coin, let us say a particular coin here. Now, this coin's bias is only determined by the data corresponding to y equals 1, the spam emails. Now, even in the data corresponding to y equals 1, we only have to look at the corresponding feature. Let us say this is feature number 5, which means you only look at word number 5 in each email and see whether that word is present or not, because you just tossed a coin for all the 1000 emails to determine not all the 1000 emails, all the 500 emails or 600 emails, let us say the spam emails, and let us say 600 spam emails, 400 non-spam emails. For the 600 spam emails, this coin was tossed. So, 600 times this coin was tossed, and then we are asking, well, we saw certain number of times this word occurred, certain number of times this word did not occur. So, what would be the best guess for this? Well, the best guess is then going to be as follows. So, it is going to be sum over I equals 1 to n, the indicator of the feature fj. We have been using the terminology fj to indicate the jth feature. Fj is a variable which takes value either 0 or 1, where it indicates the presence of the jth word in the email or not. Fj equals 1 and yi equals, so f the ith data point, the jth feature is 1, and yi equals y divided by sum over I equals 1 to n, indicator of yi equals y, right. So, if yi is 1, then this just the denominator is just the number of emails with label y. Let us say y equals 1, which means that this is just the number of spam emails, and among the spam emails, what we are asking is number of emails that had both the label as spam and had the feature, the corresponding feature, right. So, basically we are just looking at the fraction of the whole thing is just then the fraction of y labeled emails that contain the jth word, right. So, you are just counting the number of times the word occurred in spam emails and then dividing it by the number of spam emails, right. So, if your y is 1, if your y is 0, then you are counting the number of times the word occurred in a non-spam email divided by the number of non-spam emails. Basically, it is the fraction of y labeled emails where y can be 0 or 1 that contains this particular word jth word, right. So, that is basically what this guy is, right. So, this maximum likelihood estimate is going to be, of course, if y is 0, so then this, I mean, you look at non-spam, otherwise you look at spam, right. So, that is clear. Okay. So, now this gives us the 2D estimates and 2D plus 1 estimates, and because we have the estimate for this is 1, right. So, this is for all for all j in 1 to d and for all y in 0 comma 1, that is for both spam and non-spam versions of the coins for all the d coins, right. This is 2D values and then this p hat is 1 value. So, we have the 2D plus 1 estimates, which is good. So, now the very interesting thing about this model is that all your maximum likelihood estimates are just counting estimates, counting based estimates. You are just looking at fraction of spam emails, you are just looking at the fraction of emails that contain a particular word among spam emails and so on, right. It's very easy to do these estimates, right. So, now given a bunch of data, we can calculate these 2D plus 1 estimates very quickly. Fine. So, now what we have done so far is we said that we had binary data, we put down a model, we wrote down the likelihood function, and then the maximum likelihood estimates are easy to derive, and we did this in closed form. All 2D plus 1 parameters have closed form estimates, that is great. So, now what do we do with these estimates? That is the main question, right. So, how should we use these estimates to eventually, our goal is to make predictions on a test data point, right. So, you are given a new email and you are asked to ask the question whether this email is spam or not, which means that we must develop a way to use these parameters to make our test prediction. So, let's see how we would do that, right. So, now prediction. So, the next thing we need to ask, and the most important thing is how do you use this for prediction? Well, what is prediction, right? So, how would you predict? So, you are given X test. What is X test? X test is an email which has been converted into a 0, 1D vector, like how we did it for the training set. So, you are given this 0, 1D vector now as a test data point, which may or may not be present in your training data. Now, what is y test? Y hat test rather, right. So, what is our prediction for this new email X test? Well, how would we predict this, right? So, what is the most intuitive way to predict this? Well, we are going to do the following, right. So, we are going to see what is the probability that y test equals 1 given X test. I am given this email. So, given this email, what is the chance that the label for this email is 1, right. So, if that label happens to be greater than the probability that y test equal to 0 given X test, what does this tell us? This tells us that conditioned on the fact that you have seen the email X test, you are asking whether spam has high probability or non-spam has high probability. If it so happens that probability of y test equals 1 is higher, then we would just predict y hat test equals 1, otherwise we will say 0, right. So, 0 otherwise. So, this is going to be our prediction rule. It is a very natural prediction rule. And this is in some sense the best you can do, right. So, because your goal is to somehow predict y test, and then you will among the two classes, and you are going to always intuitively predict the class which has the higher probability of showing up, given that you've observed the features. So the question though is, we have not modeled P of y given x in our model. Remember, what we modeled is P of y and P of x given y, which gave us, the goal was to come up with a generative model, which means we had to model P of x comma y, and we said that we will model P of x comma y via modeling P of y and P of x given y. But now we are asking the question, we need to know the answer for P of y given x. We modeled the probability of labels being spam, that was step 1. Step 2 was, given that it is spam or non-spam, what is the probability of seeing a feature? That is what gave us the model. Now we are asking a slightly different question. We are asking, given the features, what is the labels probability, right? So which is P of y given x. But how can we get this, right? So so what can we do to get this probability, right? So let's see how we can get this probability. So how to obtain P of y given x from P of y and P of x given y. Now, what do we know to do this, right? So, well, we already know a powerful way to transform P of y and P of x given y into P of y given x, which is given by what? I mean, this is a good time to pause and think. You should already know this, right? So, this we can get using the Bayes rule. So, what does the Bayes rule tell us? The Bayes rule tells us that the probability of y test equals, let us say, 1 given x test can be written as probability of x test given y test, well, equal to 1 multiplied by the probability of y test equals 1 divided by the probability of x test. This is our standard Bayes rule. Now, what can we do using this? Well, this is probability of y test equals 1. Now, what is probability of y test equals 0 given x test? Well, this is simply going to be the probability of x test given y test equals 0 into probability of y test equals 0 divided by probability of x test. Of course, this is going to be 1 minus the probability of y test equals 1 given x test, but we can write this like this. Now, our goal is to see which of these guys is greater. That's what we want to find out, right? So, because if this is greater, then we predict 1. If the second term is greater, which is if y test probability of y test equal to 0 given x test is greater, we predict 0, right? So, we just have to compare these two terms. Now, because we have to compare these two terms, now if you notice, the denominator of both of these guys is the same, which means it does not affect our comparison. It is just a positive number which we are dividing it by. So, it typically does not affect our, it is a probability, it does not affect our comparison. So, which means that what we could do then is we can just compare the numerators and see which of these numerators has a higher value, right. So, how do we then compare the numerators? So, which means that we need to find out the values, probability of, use the blue color, probability of, let us say, x test equals, well, given x test, whatever x test is given to us, given y test equals 1 into probability of y test equals 1. First, we need to find this, right. So, and then we will find out probability of x test given y test equal to 0 into probability of y test equal to 0, right. So, but how will you find this, right. So, where is this going to come from? Well, now let's think of this, right. So, if you think of this, so let's say I am going to write x test as f1 f2 ft. Now, it is some binary vector, right. So, if you want to think of it as numbers, think of it as 0 1 0 0 1, right. So, some binary vector which corresponds to the email that is given to us. Now, given y test equals 1 into probability of y test equals 1. this is what this is, right. So, but now because our model assumes class conditional independence, now this probability can be written as the product of I equals 1 to d. Well, now you plug in your estimates, right. So, you need to know the probability with which a particular word was generated, but now your training maximum likelihood tells you a best guess for it. Now, we will plug in those estimates, right. So, we will just say this is p hat 1, p hat, yeah. So, 1, let me call this j, p hat 1 j power f j into 1 minus p hat 1 j power 1 minus f j. Well, if you remember, this is just exactly the likelihood function which I had written earlier, but then there we were thinking of p as a variable, but now here we are saying that we will use the maximum likelihood estimates, because that is our best guess for p's. We have those parameters estimated, we will use that here, plug in that here. So, that multiplied by, now what is our best guess for p, probability of y test equals 1, well that is just p hat. These are the parameters that we estimated, right. So, now you are using basically d plus 1 parameters here, d parameters here, 1 parameter here. We are not using the parameters corresponding to y test equals 0 here, because this, in this particular case we are trying to calculate it for y test equals 1, right. Okay. So, this number you will calculate. Similarly, you will calculate the other number which is for y test equals 0, and now we are going to see which is bigger. Now, which means I am going to say check if probability of j equals, I am going to write the same thing again, right. So, 1 j power f j into 1 minus p hat 1 j power 1 minus f j into p hat. If this is greater than, right. So, let me not say check, if it is greater than, what is going to be the similar value for y test equals 0? Well, that is going to be product of j equals 1 to d, but now we are going to use the coins that we have estimated on the spam side and the non-spam side, which is p hat 0 j, which can be completely different value from p hat 1 j, remember, power f j into 1 minus p hat 0 j power 1 minus f j multiplied by, now this is going to be the probability of y test equals 0. What is our guess for probability of y test equals 0? Now, pause and think about it, it is not too hard to see. If probability of y test equals 1 is p hat, then our best guess for probability of y test equals 0 is just going to be 1 minus p hat, right. So, now if this happens, if you calculate these two terms, now you can calculate these values exactly, right. So, because remember our x test is, let us say 0 0 1 0, then this means that this is f1, this is f2, this is f3 and this is f4, right. So, we have 4 features and these are the feature values. The features enter into the picture here, right. So, this is what decides the features. This side, this is what is not decides, this is where the features come into the calculation. The parameters that you have estimated come into the calculation everywhere else, right. So, now these are the underlined places are where the parameters that you have used, you will plug it in, which means that you can calculate these two numbers and then check which of these numbers is larger for the given x test, and you predict, well, if this has happened, implies predict y test, y hat test equals 1, else y hat test equals 0. Now, this would be our prediction technique, right. So, this is a very simple algorithm now, right. So, you just do the maximum likelihood estimates, which was super simple. You just have to do fractions, countings and so on by looking at your data set, and once you have the counts, now you just look at, use the Bayes theorem to convert these parameter estimates into reasoning about probability of y given x, and then see which of these terms is larger and make a prediction accordingly, right. So, it's an extremely simple algorithm, and now it's a good time to give a name to this algorithm. We have not given a name to this algorithm. So, the name comes from the fact that the model uses two main assumptions or two main things. One is there is a class conditional independence assumption, and this is the most important thing in this model, which was used to reduce the number of parameters from 2 power d to 2d, right. So, the second one is, well, you use the Bayes theorem to make a prediction, right. So, you get the estimates, but then you use finally the Bayes theorem to flip your estimates from x given y to y given x, and then make your prediction based on the Bayes theorem. Now, this class conditional independence assumption, as I mentioned, says the following. In the example that we looked at, it says that if you know it's a spam email, then knowing that the word lottery has occurred does not influence our uncertainty about whether the word money occurs or not. Now, in practice, this may not necessarily hold, because if I told you it's a spam email and I also told you that the word lottery has occurred, now suddenly your uncertainty about the word money or dollar might actually go up, right. So, you might think that, well, lottery has come there, it's a spam email, so probably this value should also be there, right. So, your likelihood might go up, right. So, which means that there is potentially some correlations between these two random variables, the random variable that decides the word lottery and the random variable that decides the word money. However, we are saying that these two random variables are completely independent of each other, right. So, given that this class is spam, similarly for the non-spam class as well. This may not necessarily hold in practice. So let me make that comment, so that this may not hold in practice. First point. So, it's a naive assumption, right. So, it's one of a simplifying assumption, it may not hold in practice, but we should also mention that, you know, this algorithm still works pretty well in practice, especially when your number of dimensions is large, right. So, when you are dealing with dictionary size dimensions, these correlations do not seem to matter so much in prediction accuracy with respect to real world data sets. So, in practice, this is a reasonably good algorithm, though we are making this naive assumption, and of course, we are using the Bayes theorem to finally make the prediction. So, the algorithm itself is named after, you know, using these two key things that this the key properties that this algorithm uses, and this algorithm is what is called as the, you know, the naive Bayes algorithm. So, this is the name of the algorithm, it's called the naive Bayes algorithm. Naive because the class conditional independence assumption is pretty naive, and Bayes because, well, it's a generative model where you are modeling p of y and p of x given y. So, you have to use the Bayes theorem to get p of y given x, which is what is the real quantity of interest for prediction purposes. So, yes, so this is the name of the algorithm. So it's a very popular algorithm, very simple but effective algorithm.